Terms take two functions and map them with respect to each other, similar to how a function will take and map the x values to the y values. With a Fourier transform, what we would do with that is we could take a function with respect to the frequency and turn it into a function with respect to time, or vice versa if you're doing the inverse. So I would take that function with respect to time, it's equal to the Fourier of the function with respect to the frequency. And the way I would do that is the integral from negative infinity to a positive infinity of the frequency function times e to the I omega t, or if you think through it, omega as that 2 pi frequency value. Where we would use that would be when we're talking about waves. So if I have these three waves that are all combining through interference to create this function with respect to time, then the Fourier transform would pull and convert this time into a frequency function where we can see these sharp spikes here that tell us what the different frequencies are that are part of that wave. The Laplace transform, on the other hand, is a more general version of the Fourier transform. So I would take that function with respect to time and turn it into any function with respect to this s variable that we have. So I would say that function with respect to s, the Laplace transform of t, I would do very much similar to what we did over on the left-hand side here, where we would have the function with time times e to the negative st dt. If you want to see a sample of that, this is sort of the worked out version of the function EAT, which would come out to become this fraction over here, the 1 over s minus a. So that would be equal to e to the at. It would be important to note that in this case that the s would have to be greater than a because of that e value for that. So the Laplace transform turns ordinary differential equations into algebraic equations just so that they can be solved more easily. And the Fourier transform is a more specific version of